This is a University of Otago podcast.
All right, everyone. Welcome back to the third session of the Bite-Sized Science for the New Zealand International Science Communication Festival, or Science Festival, I should say. So for the first session back, we've got Jack Williams and Loren Matthewson, who are going to be looking at the stresses and strains of drilling into the Alpine Fault, and so they just give us their short talk. So take it away.
Okay. Can you hear me? Is that on? I'm good. Okay, good afternoon, everyone. Thanks for coming. So some of you may be aware, here in New Zealand, we're actually on the boundary of two tectonic plates, have the Australian plate out to the west and the Pacific plate out to the east. And they're moving with respect to each other at a speed of about 37 millimeters a year or so on the South Island. And here on South Island, most of that motion is accommodated on just one structure we call the Alpine Fault, which, as you can see on the map there, runs along the west coast down through South Island. So this motion is it's a combination of horizontal motion, what we call strike slip, where the plates are kind of moving like this with respect to one another. And there's also an element of the plates colliding with one another. And the Pacific plate is actually being forced up the Alpine Fault and forming the Southern Alps mountain chain. Now, the way that this motion occurs is what we call endogenous stick-slip behavior, where essentially the plate will appear stuck for long periods of time and there's no motion across it. Up in the north section of the fault, they built a wall across it in the 1960s, and to this day, that wall has not moved a single inch. And then suddenly, it will slip very quickly in an earthquake. And we have really pretty good evidence on the Alpine Fault that when it slips big time. In probably about magnitude 8 earthquakes. What's really interesting for the Alpine Fault is that these occur at fairly regular intervals, on average about every 330 years. Now, given that the last one occurred nearly 300 years ago in 1717 AD, that means that we are coming up to a period now where an Alpine Fault earthquake is actually quite likely. Currently, the latest estimate is a 30% chance in the next 50 years. And I said, these are big earthquakes. So we predict that when the Alpine Fault slips in its next earthquake, the rocks on the Pacific plate side, so those on the southeast of the fault, they're going to move about 8 meters horizontally, and they'll move about 1 meter vertically up. This is some of you may recognize, this is Franz Josef. That red line is the Alpine Fault itself. It runs straight through the petrol station there. They're definitely going to know about it when it goes off. So why do we want to drill into active faults? This is the Alpine Fault exposed at a place called Gorn Creek. It's reasonably well exposed there. So what can drilling tell us that we can't get from just looking at the fault itself? Well, for us as scientists, what's really important is that earthquakes, these are processes that fundamentally they occur at depth. This is kind of where they start. And so as scientists, for us to get the best possible kind of data from them, we really want to be able to drill into them and get direct observations. So collect samples from the fault and look at their chemistry and their mechanical properties, look at the fluids that are circulating around the fault, measure the temperature down there, and also the stress state, so essentially how the movement of the plates either side of the fault is loading the fault. And these are all really important parameters that will determine when the next earthquake is going to happen. We can also build long-term observatories down there, and we can collect data over years and decades about the fault. And for these reasons, globally, there's been actually quite a number of fault zone drilling projects in the past 10, 15 years. What makes the Alpine Fault drilling program different is that here we're drilling a fault kind of in the run-up to an earthquake. Most of these other drilling projects, such as the one, the JFAST, so the 2012 Tohoku earthquake, that was sampled a year after the earthquake. So they're kind of sampling faults just after an earthquake. Here, Alpine Fault is one of the few places in the world where we can have, a fairly high confidence that there's going to be an earthquake some point in the next few decades. So this makes it really a worldwide important study. And so this is kind of the reason that the Deep Fault Drilling Project, as it's known, kind of got set up. So this is kind of a multi-phase program. It's international. It's teams of about 100 or so scientists involved with this. The first phase of which occurred in early 2011, where we were able to drill 2 vertical boreholes that sampled the fault. So this is a cross-section through the site where we drilled. And essentially what you can see there is you can see the faults at the surface and how we've projected as it goes down through the Earth and where it got intercepted by those 2 boreholes. Some of the cool data we got from this is that you have quite elevated temperatures and also really low permeability, so fluids are finding it really hard to flow around the fault. This is just some of the work that I've personally been doing. The work that I do is only a very small element of this project. And this is kind of imaging the rock core that you collect from this project. So all that rock core was taken to the hospital here in Dunedin, and we scanned it on the CT scanner there. I've also been scanning it with some neutrons as well, and this has given me a really good idea of the different types of the structure in the rock and the different minerals in it. So I now hand over to Loren. You can talk about the latest phase of this project.
All right, can you hear me? Awesome. So I'm Loren, and I'm a master's student at Virginia Toys. And so I was involved in DFDP2, the second phase of the deep fault drilling project. And so what we had was this massive phase of, after DFDP1. So we had all this preliminary science, or it was really good science, but we really wanted to go deeper and figure out what was happening in the seismogenic zone. So when earthquakes occur at depth, we wanted to drill down into there and figure out what is happening here. So we aimed to drill about 1 kilometre into the earth to the fault and sample the fault and what happened on the other side of the fault. So right through and get samples way down there. So I was part, and Jack was too, of a science team which was over 100 scientists, all from all over the world, all involved in this massive project. So here we can see just a simple block diagram. So we've got the Australian plate and the Pacific plate. So at the moment, we're on the Pacific plate in Dunedin. So the Pacific plate is pushing over, like Jack said, making the Southern Alps, and we wanted to drill down through the Pacific plate, right down into the Alpine fault and through into the Australian plate to figure out what was happening. So you can see these arrows here. Ooh, I can't really see what's happening. The arrows are pointing upwards, so the rock itself is crushing up that Alpine fault and up into the surface. So lately, well, before the drill project, we had done a lot of surface samples and deep DFDP1 sampling, and we wanted to see what those same kind of rocks are doing way down where the earthquakes were occurring. So that was the main aim of DFDP2. So here's a pretty picture of DFDP2 in action. So we've got the drill rig in the middle there, and one of those rare sunny days on the west coast without rain. And I'll be talking a little bit about rain later, so to soak in the view of what we didn't normally see. Cool. So the deep fault drilling project phase 2 didn't end on a super big high, unfortunately. We had a lot of technical difficulties, but that was really thought about a lot before we did the project, that it was a really new thing to drill into this schist. So it's really hard rock and drilling into the Alpine fault. It was a pretty pioneering project pioneering project in New Zealand. So we did have some engineering problems, but we still managed to soak out a lot of science from the project itself. So you can see our supervisor walking past some concrete core here. She's looking a little bit less than impressed, and I think it was the general feeling of seeing that core there was a pretty sad one. But here we have one of the main reasons why this was super exciting. So you can see on the right there, we've got two guys getting pretty soggy for the sake of science. And that water that's spilling out of the borehole there, it was over 30 degrees. So we'd only drilled about 200 meters down to that point, and it was super warm. And so we were wondering, why is it so warm so quickly? And it just continued to get hotter and hotter as we drilled down. And so they're getting some water samples, and they're going to send them away and get some chemical analyses done on that. So here's some more exciting stuff about the temperature gradients. So you can see the DFDP2b, that geotherm there, so 100 to 200 degrees Celsius per kilometre. So that's a really, really hot thing. So when you boil your jug, it's 100 degrees Celsius. That's pretty hot. But to get that hot in the earth so quickly is pretty amazing, and it's actually one of the hottest boreholes, the top 1% of hottest boreholes in the world. So comparing it to the global average geotherm, so how hot it is per kilometre, the typical geotherm is only 25 degrees per kilometre. So this borehole is hot, super hot. So it also had all these fluid pressures, and we were just wondering, how on earth can this borehole be so hot? Wow, here's the answer. So this is from GNS, this wee schematic here. So what happens is the rain comes down. Unlike that pretty picture I showed you before, it's normally raining into the mountains, and it's coming down into the mountains as cold water. But what is also happening is, because what Jack said, the rock is pushing up, so the Alpine fault's lifting up this hot rock, it doesn't have time to cool. So when the rain's coming down into the mountains, it starts to heat up. The rock heats up that water, and it's getting squeezed. Because of the Alpine fault, it's not letting any water past it, so it gets squeezed, this hot water, and it actually gets funneled into the valleys. So when we were drilling in this valley, the Whataroa Valley, we found these really, really hot temperatures and pressures. So that was a really, really, really cool result. And we've actually got a paper coming out pretty soon about that. So yeah, thank you so much to our sponsors, and if you've got any questions or we haven't said anything and you're interested in anything at all, please ask away.
Cool. Okay, thanks very much for that. That was really interesting. Does anyone have any questions about this drilling? Yeah. No, that's okay. I'm curious, what was the significance of the concrete cores and your depressed supervisor?
So what had actually happened was, when we wanted to cement the casing, so when we drilled down, you have this open hole, right? So you've got all the rock around the edges. We wanted to make sure that borehole wasn't going to cave in on itself because of the high temperatures and pressures and things. So we put this casing down, and we wanted to cement along the outside of it. But what had happened is some of the casing had broken, and it actually let concrete into the hole itself. And so what we're attempting to do was to core down through the concrete and actually get some more rock core. But unfortunately, that broken casing was just a little bit too much. The technical comparison, trying to get past that was going to cost a lot of money, and it wasn't really doable in that kind of time frame around Christmas time. So it was an abandoned borehole situation. And so getting the rock, getting that concrete core to the surface was a definite end to the project itself.
Across so you have the climb, so where the two meet. Mm-hmm. Do you get differential pressure at the top of a fault, sort of near the surface, and at the bottom of the fault? And does that significantly affect the chances of something popping off?
Like the difference in fluid pressure either side of the fault, is that what you say?
Not either side of the fault, but at sort of the bottom of the plate versus the top of the plate. So, ground level versus 1,000 metres down, across that, where the fault meets. Do you get differential pressure at different heights? And does one signify something else? So if you've got a higher pressure on the plate at 100 metres versus a higher pressure at 1,000 metres.
Oh, I see what you're saying.
I don't think anyone can really... You need really high-resolution stress measurements. And so, I don't think anyone really knows is basically the answer to that.
Right.
I think if you were talking about on a scale of kilometres, you could say that differential pressures would be the difference between being in a seismogenic zone and perhaps being in somewhere where it's really, really hot, and you would have different mechanisms going on with an earthquake there. Would be the only thing that I could think of.
The thing about the Alpine fault that's really interesting is the fluid pressure is really... The fault's an impermeable barrier. It's a really clay-rich layer, so fluids can't go across them. And so that's why the fluids get focused up the fault. So when we drilled in DFDP1, once we got through the fault, there's big difference in fluid pressure either side, so all the fluids in the hole just got sucked into the bottom of the hole because the pressure beneath the fault was so much lower.
Thanks for that. That's really interesting. So we're just going to grab the next talk if it's around.